Okay, part 2 of the geometric sequences. So example 3, determine whether each sequence is arithmetic, geometric, or neither. If it's arithmetic, find the common difference, that D, and if it's geometric, find the common ratio, or R. All right, so if you look at this one, you can calculate the first few terms in there if you want. So if you let n equal 1, that would be -3, n equal 2, -1, n equal 3, 1, n equals 4, and you get 3, and it keeps going from there. So if you look at your terms, is there a common difference? Yes. And what is it? Well, the common difference would have to be 2. Well, if there's a common difference, what kind of a sequence is that? Arithmetic. Anything that looks like it's a linear type of a function, that's going to be arithmetic, just FYI. So if it would graph you a line, you've got an arithmetic sequence. All right, part B. 1, 1, 2, 3, 5, and 8. Well, I'm not multiplying the same thing every time, and I'm not adding the same thing every time, so this would be a big ol' neither. Anybody know what kind of sequence that is? I see everyone's hands up, going up in class. That's right, that is the Fibonacci sequence. By good old Fibonacci. So it is recursive because you just add the 2 previous terms to give you the next one. So 1 and 1 is 2, 1 and 2 is 3, 3 and 2 is 5, 3 and 5 is 8. So the next term would be 13. Okay, part C. That looks really familiar to that. So that is geometric. And your R, that common ratio, is the thing with the power on it. It's 5/4. Now you might be going, well, wait a minute, that doesn't really look like this. Doesn't it have to have a power of n-1? Well, yes it does, but we can kind of play around with it. I can split off a 5/4. And that makes it 5/4 to the n-1. Because I didn't, like, well, how'd you know it was -1? Well, how many 5/4 did I pull off of there? 1. So n-1. If I would have pulled off 5/4 squared, this would have been n-2, because the power was 2. Okay, example 4. Find the 5th term and the nth term of the geometric sequence where you start with 1 and your ratio is -1/3. So let's flip that. Let's get the nth term first, just because. So I'm starting with 1. My ratio is -1/3. And I'm going to raise it to the n-1 power. So my nth term is really just -1/3 to the n-1. So now I can use it to give the 5th term. So plug in 5 for the n. So that's -1/3 to the 4th, which is 1/81. And if we were in class, you'd all be going crazy, like, wow, he's doing magic. It's math magic. I'm a math magician. Ha, 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 ha. I think I've been making videos for far too long. Getting a little punchy. Okay. Now, geometric sequences, the reason why I like them is just because of their sums, especially not so much for like a finite sum. Like you can get the sum using this formula, it's not that bad, but the fun ones are the ones that are infinite. So let's do the finite and then we'll get into the infinite. So example 5, find the sum. So we're just going to follow out this formula here. So whether they write it like this or in the sum format, you can just use that right there. So the first term is 6, that's the A. And then 1 minus your R is 2. And I found another little typo. Instead of an N right there, that should have been 10. Because if you notice in the formula, this is always 1 bigger than the highest exponent. It's n minus 1 there, and it's n in the sum. So if it's 9 on the sum notation, it's going to be a 10. And the 10 would get repeated over there. And then 1 minus r is underneath. So now we just have to work this stuff out. So 2 to the 10th is 1,024. So if you subtract, divide, and then multiply by 6, you end up with 6,138. All right, I'll stop this video here, and in the next one, we'll look at infinite sums, or infinite geometric sums.